So we know that a union of sets A union B is equal to X such that X belongs to A or X belongs to B. So it can be if all the elements that is in A and all the elements that is in B. So A union B consists of all those elements that is in A and that is in B. And that's how we represent it. Or so if X belongs to A, then also it belongs to A union B. Means if X belongs to A, then also it belongs to A union B. Or if X belongs to B, then also it belongs to A union B. As you can see, for any element X, if that happens to be this element or this element or this element, then it belongs to A. It may happen to be here, it may happen to be here. So all of these elements, they belongs to A. And if they belongs to A, then they belongs to A union B. Because clearly A union B is A, superset to A. So A is a subset to A union B. A is a subset to A union B. Similarly, B is a subset to A union B. B is a subset to A union B. So this is one of the set operation, which is A union B. So in this set operation, to the set A, in your resultant set, what is happening is that to the set A, you are adding some other elements of another set, which is B. So you are adding the elements of another set, which is B. That is what A union B is. Similarly, B union A, we know that union is commutative. So in B union A, to the set B, you are adding the element of A also, and the resultant set is your B union A. Now let's look at intersection. The intersection of two sets, which is A intersection B. This is X such that X belongs to A and it also has to belong to B. Let's say this is X. Then X does it belongs to A? Yes, this is true. X belongs to A is true. But X does it belongs to A intersection B? No. So X belongs to A, but X does not belongs to A intersection B. So in union, if X belongs to A, it means it belongs to A union B. But that's not the case with intersection. Of course, because the intersection region is this one. This is your intersection region. This is your intersection region. What if you have here Y? Then Y belongs to B. But Y does not belongs to A intersection B. But any element X, let's say here I am taking it to be Z. There's one arbitrary, any element in this region, Z. Or for every element Z that is in this region. So for every Z that belongs to A intersection B. If Z belongs to A intersection B, then Z belongs to A. Yes, of course. And Z belongs to B. You know, this is the way to prove this is the way to prove any set is a subset to other set. What is it? You take any for all element that belongs to this set. Okay, if you want to prove that a set A is a subset of B, then how do you prove it? You prove it by taking any element in A, and then you show that that element is also does also belongs to B. So you take, let's say, X belongs to A, and with multiple step of inferences, you have to show that it ultimately shows X belongs to B. So for if for every element of A it also belongs to B, then A is a subset of B. This is one of the way to show if any set is a subset. So here also, if you can see, I am just taking any element Z in that region. So for any general element Z, so any Z that belongs to A intersection B, or all Z that belongs to A intersection B, then it belongs to A also and it belongs to B also. It means that A intersection B is a subset of A and A intersection B is a subset of B. I have both ways of showing in this board right now. So on one side you have Venn diagram, on the other side you have this approach. If there was no Venn diagram also, then in this inference is enough to tell you that okay, A intersection B is a subset of A and A intersection B is a subset of B. Likewise in the union case, A is a subset of A union B and B is a subset of A union B. So these are the two ways to deal with set problems. You can either look from the Venn diagram, which is pictorial representation, and this will give you very easy. I have already told you that using Venn diagram it is like, oh, it's obvious. And this is also another method because this is inference method. Even this, it means this, it means this. Oh, it means this. Okay. So what we can say from this is that A intersection B is a subset of A and A intersection B is a subset of B. Now let's look at complement. A complement is equal to X such that X does not belongs to A. This is my complement. X such that X does not belong to A. So take any element here. Let's say this element is any element X that is in A. So if X belongs to A, clearly X belongs to A. So X belongs to A means what? This is your A complement, right? Everything apart from A, anything outside of A. So if X belongs to A, then X does not belongs to A complement. Okay, and for any element Y that belongs to A complement region. So Y belongs to A complement, then Y does not belongs to A, right? So A and A complement they are not subset of any of one another, because for any X that you are taking, that X does not belongs to the other way. But there is no intersection region also, because if for every X that belongs to A, you do not find any X that also belongs to A complement. For all X that belongs to A, that X belongs to, that X does not belongs to A complement. And for all Y that belongs to A complement, that Y does not belongs to A. So A and A complement are disjoint. So A and A complement are disjoint. A and A complement are disjoint. So we have seen that if for two given sets, if we have to show that this set is a subset of the other set, Let's say there is set A and set B, and you want to show or you want to check whether set A is a subset of set B. Then how do you do that? Is you take any element x that belongs to, you just do this, that x belongs to A. Okay, and because of means this is given now, and from it you take you can make many inferences, and if you get that x belongs to B, then it means that A is a subset of B, because this x is any element of x, you know, because you are not taking a particular element in x, you are taking any x in A, any any x in A. Then for any x in A, if you are getting that x to be in B, it means it applies for all elements, right? So in a similar manner, if using this process, if you get that x does not belongs to B, it means that A and B has more elements in common, right? So A and A complement are disjoint, and this A and A complement are disjoint in a manner that they are partition. This is a new term, partition. What is a partition? Uh, Partition of universal set. So a set and its complement partitions the universal set. A and A complement are disjoint. A set and its complement partitions the universal set. Partitions the universal set. What is a partition to a set? Um, if you are dividing the set into multiple sets such that all of those sets, the union of all those sets will give you the set itself, but they all are mutually disjoint. If you take two arbitrary sets, this is A and this is B. Okay, you know what is A union B is. You know what is A union B is. But let's say I divide this A union B into regions. Into regions like this region. This region is 1, this region is 2, and this region is 3. Okay, so this 1 and 2 are mutually disjoint, there is no elements in common, and 2 and 3 are mutually disjoint, there are no elements in common, and 1 and 3 are mutually disjoint. What I mean is, what I mean is this is one region, this is region 1, this is region 2. Okay, this is region 3. So they are mutually disjoint region, and 1 union 2 union 3 is nothing but A union B. 1 union 1 union 2 union 3 is A union B. So what we say is that 1, 2 and 3, they are partitions of A union B. Similarly, any set with its complement is a partition of universal set. So a set and its complement partitions the universal set, means that A union A complement is equal to universal. So if you are given an expression that involves many set operations, uh, like for example, expression can be something like this: A union B uh, intersection B union A Actually, this will give you nothing but A union B, right? So, but this is one expression in which you have different set operations, and some set of operations, the precedence will be that first you compute this, then you compute this, and then you perform the intersection between the two, because these are the braces. Braces have higher precedence. Similarly, some other set operations like A uh, intersection B union C. So one method of getting to the solution is Venn diagram. The another method is that you start with this, that okay, if this is the set given, then you start with, okay, X belongs to A intersection B union C. Then you can make some conclusions from it. It must belongs to A, and it must belongs to B union C, because that's the definition of intersection. You know that. Okay, let me write the definitions, all of the definitions at one place. So then we can look at different expressions, and we can directly, as a cheat code, we will look at what is the inference because of union, and because of intersection, what is the inference because of union. So this is what you know. So from here you can get that X belongs to A, and so first point is X belongs to A, you know that. X also has to belong to B union C. Now B union C means that X belongs to B or X belongs to C. So this is your first jump from this set. This is your first inference. Now from this is your second inference. From here now this is your third inference. Okay. So this is one part, that X belongs to A, and this is second part, that it does not only have to belong to A for X to belong to this. It also has to belong to either B or C. Let me write all of the formal definitions of union intersection in this format.